Hello today, we are going to learn rendering in graphics. In Module 4 we have these topics: ray tracing versus rasterization, raycasting and intersection testing, global illumination and radiosity shadows, shadow mapping, shadow volumes, reflection and refraction. Ray tracing and rasterization are two different techniques used in computer graphics to render 3D scenes. While both techniques can produce high-quality images, they use fundamentally different approaches to generate the final image. Rasterization is the most common technique used in real-time applications such as video games. It works by dividing the 3D scene into a set of 2D polygons and projecting these polygons onto a 2D screen. Each polygon is then shaded and colored based on its properties, such as its position, lighting, and texture. The final image is generated by rasterizing, or converting, the polygons into individual pixels and displaying them on the screen. In contrast, ray tracing works by tracing the path of light rays through a 3D scene to generate the final image. It simulates the way light interacts with surfaces in the scene. By tracing the path of light rays as they bounce off objects and interact with the environment, each pixel in the final image is calculated by casting a ray from the viewer's eye through the 3D scene and determining which objects are visible along that ray. This process involves complex calculations and can be computationally intensive, making it more suitable for offline rendering or high-end graphics applications. The main advantage of ray tracing over rasterization is that it can produce more realistic and accurate images. It can simulate complex lighting effects, such as reflections, refractions, and shadows that are difficult to achieve with rasterization. However, this comes at the cost of increased computational complexity, making it slower than rasterization for real-time applications. In recent years, there has been an increasing interest in real-time ray tracing, which aims to combine the realism of ray tracing with the speed of rasterization. This has been made possible by advancements in graphics hardware, such as introduction of dedicated ray tracing hardware, as well as improvements in algorithms and techniques for real-time ray tracing. Raycasting and intersection testing are two important techniques used in computer graphics and related fields for tasks such as rendering 3D scenes, collision detection, and ray tracing. Raycasting involves tracing a ray from a given point, such as the camera, through the 3D scene to determine what objects are visible along the ray. This is done by testing for intersections between the ray and the objects in the scene, and calculating the color and shading of each intersection point. Based on the properties of the object and the lighting conditions in the scene, raycasting can be used for real-time rendering, but is less accurate than ray tracing and cannot simulate more complex lighting effects, such as reflections and refractions. Intersection testing involves determining whether a given ray intersects with an object in the scene, and if so, at what point. This is done by calculating the intersection point between the ray and the surface of the object using techniques such as the Muller-Trumber intersection algorithm or the Gilbert-Johnson-Kurethy GJK algorithm. Intersection testing is commonly used in collision detection, where it is used to detect whether two objects are intersecting and calculate the point of intersection, which can be used to determine the appropriate response, such as bouncing off or breaking apart. Raycasting and intersection testing are often used together in ray tracing, where the goal is to generate a high-quality image by tracing rays through the scene and testing for intersections with objects to determine the final color and shading of each pixel. In this context, raycasting is used to trace rays from the camera to the scene objects, while intersection testing is used to calculate the intersection points between the rays and the objects in the scene. These intersection points are then used to calculate the final color and shading of each pixel in the image. Global illumination and radiosity are techniques used in computer graphics to simulate the way that light bounces around a scene and affects the color and brightness of surfaces. Global illumination refers to any technique that attempts to simulate the interaction of light with objects in a scene in a realistic way. This includes techniques such as ray tracing and radiosity. Global illumination is important for creating realistic images because it takes into account the indirect lighting effects that occur when light bounces off surfaces and illuminates other objects in the scene. Radiosity is a specific technique for simulating global illumination that focuses on the way that light is reflected between diffuse surfaces in a scene. It works by dividing the surfaces in the scene into small patches and calculating the amount of light that is reflected from each patch to every other patches and calculating the amount of light that is reflected from each patch to every other patch. This calculation takes into account the color and reflectivity of each patch, as well as the position and orientation of the surfaces in the scene. The final result is a set of equations that can be solved to determine the color and brightness of each patch in the scene. Radiosity is commonly used in architectural visualization and other applications where the accurate simulation of lighting is important. However, it can be computationally expensive and may require significant processing power and memory to achieve realistic results. There are also many variations and extensions to radiosity, such as hierarchical radiosity and adaptive radiosity, that aim to improve its performance and accuracy. Overall, global illumination and radiosity are important techniques in computer graphics that can greatly enhance the realism and quality of rendered images by simulating the way that light interacts with objects in a scene. Shadows are an important visual cue that help to convey depth and realism in 3D scenes. Two common techniques used to simulate shadows in computer graphics are shadow mapping and shadow volumes. Shadow mapping works by rendering the scene from the perspective of the light source, creating a depth map of the scene from the light's point of view. This depth map is then used to determine which parts of the scene are in shadow and which are not. When rendering the scene from the camera's perspective, each pixel is tested against the depth map to determine if it is in shadow or not, and the appropriate shading is applied. Shadow mapping is relatively efficient and can be used in real-time applications, but can suffer from oleosity. Shadow volumes work by creating a volume that surrounds each object that casts a shadow, known as a shadow volume. This volume is created by rendering the object from the perspective of the light source and extruding the resulting silhouette into 3D space. When rendering the scene from the camera's perspective, each pixel is tested against the shadow volumes to determine if it is in shadow or not. Shadow volumes can be more accurate than shadow mapping, but can be more computationally expensive and difficult to implement. Both techniques have their own advantages and disadvantages, and the choice of which technique to use will depend on the specific requirements of the application. Other techniques for simulating shadows include ray tracing and radiosity, which can produce very realistic results but can be computationally expensive. Reflection and refraction are important optical phenomena that are commonly used in computer graphics to simulate the behavior of light as it interacts with surfaces and materials. Reflection occurs when light hits a surface and bounces back in a different direction. The angle of incidence, the angle between the incoming light and the surface, is equal to the angle of reflection, the angle between the outgoing light and the surface. In computer graphics, reflection is often simulated using a technique called ray tracing, which traces the path of light rays as they bounce around a scene and calculates the reflection of each ray as it hits a reflective surface. This can be used to create realistic images of reflective surfaces such as mirrors, polished metals, or water. Refraction occurs when light passes through a transparent or translucent material, such as glass or water. The path of the light is bent as it enters and exits the material, and the amount of bending depends on the angle of incidence and the properties of the material. In computer graphics, refraction is often simulated using a technique called ray tracing, or a more efficient technique called the Snell's law, which calculates the amount of bending of the light as it passes through the material. This can be used to create realistic images of transparent materials such as glass or water, or to create visual effects such as lenses or prisms. Both reflection and refraction are important for creating realistic images in computer graphics, and are often used together to simulate the behavior of light as it interacts with complex surfaces and materials. They are also used in combination with other techniques such as shading and texturing to create visually compelling images and animations. Thank you for watching us.